Have you ever wondered how those tiny chips in your everyday devices suddenly come to life and perform their tasks with precision? It is like giving a brain to a small robot or appliance. Making a microcontroller execute specific instructions involves a fascinating journey from human thought to digital action. Programming a microcontroller typically involves 5 key steps: setting up your development environment, writing the code, compiling it, flashing or uploading the compiled code to the device, and finally, testing and debugging the functionality. This systematic process ensures your embedded system behaves exactly as intended, bringing your design to reality. The distinct steps are essential because microcontrollers are specialized computing devices designed for direct hardware control with limited resources. Unlike general-purpose computers, they do not have an operating system to manage tasks or complex file systems. Every instruction directly manipulates hardware registers, making a precise workflow crucial for efficiency and reliability. The development tools translate your high-level instructions into the specific machine language the microcontroller understands. To begin, establish your development environment. This typically involves installing an integrated development environment, or IDE, such as Microchip MPLABX or STM32Cube IDE. Your IDE will come with a compiler, which translates your human-readable code into machine language, and a debugger, which helps find errors. Next, you will write your code, often in C or C++, using the IDE's editor. This code will directly interact with the microcontroller's peripherals, setting up pins for input or output, controlling timers, or communicating via serial interfaces. Once your code is complete, you will compile it to create a hexadecimal file, often called a hex file, which is the machine executable version. The next crucial step is flashing the hex file to the microcontroller. This is usually done using a hardware programmer or debugger tool connected to your computer via USB and to the microcontroller's programming pins. The flashing process writes the compiled program into the microcontroller's non-volatile memory. After flashing, you move to testing. This involves observing the microcontroller's behavior, perhaps with LED indicators, sensor readings, or serial output. If there are unexpected behaviors, you will use the debugger to step through your code, inspect variable values, and identify where the logic deviates from your design. This iterative testing and debugging cycle refines your program until it functions perfectly. Mastering these steps empowers you to not only bring your embedded designs to life but also to troubleshoot and optimize them effectively. Understanding the interaction between your code and the physical hardware allows you to create efficient, robust, and responsive systems, transforming abstract ideas into tangible working solutions.